The team members were basically Delphine Bijuru, Samson Naoko, Olive Dushime, and Paula Heza, but we also had other assistants that were assisting us in the field. So if you look at the Rwandan agricultural context, we noticed there are a lot of losses that comes from food losses and waste. That is 40% waste in a year. And if you look at the problem, the demand for agricultural products is growing, but then there are losses, like 40% losses when it comes to food products. And also the insecurity that I've mentioned. And then there's an increasing excessive use of fertilizers. And this basically leads to degradation of the environment. But then we look at our opportunity that the government is trying to improve this and working with very many companies and events to be able to help in developing solutions for Rwanda. So we took this and we developed an offline TinyML solution. So in this solution, we have a component that is able to collect soil nutrient, pests and diseases from the field, and we use that data to be able to determine when to plant and what is the minimal amount of fertilizer that can be applied, and also to give real-time alerts to farmers. So this is basically customized for the Rwandan problems and to enhance in crop monitoring and also real-time alerts. Basically, our prototype was able to evolve. When we had it initially and when we went to the field, we noticed we needed to include the local language because some farmers were not able to get us. Then there were also removal of some aspects, that is the prediction. It's like the farmers know what to plant, and also to be able to look at weather forecasting to include that. So we also ended up dividing the prototype into three sections: separate soil analysis and fertilizer recommendation, disease recommendation, and planting recommendation in different. And then for this, we now narrowed down to be able to prototype soil analysis and fertilizer due to budget and time that we had. So in our final product, we basically had the ARM Cortex microprocessor connected to the soil NPK sensor, soil moisture sensor, and also integrating forecast weather, be able to see and use that to be able to predict basically on what fertilizer should be used based on what we are able to do. So my colleague is going to present how the solution that we're able to prototype was able to work.
Welcome to this video demonstration of the working of NPK sensor. Over here we have the LCD, the board that is having all the logic and the whole circuitry, and then we have the NPK sensor and we have a computer connected to it. So we are getting 0 values here because the sensor itself is not dipped in soil, so it's reading 0 values for nitrogen, phosphorus and potassium, and giving you recommended action of adding urea, DAP, and potassium sulfate. We want to see the same output coming from the LCD, where it's displaying 0 values as well, and giving you the same recommendation as we saw on the computer to add DAP, potassium sulfate, and urea for the respective nutrients that are needed in the soil. So once again, we want to see changes on the LCD, where it changes after 4 seconds to display new values on the screen. So we see 0 values still being displayed. The next experiment we'll perform is dipping it inside the soil. Remember, initially we had 0 value, so we want to dip this in soil. We want to make sure it's steady in the soil. Then we want to see whether the values are changing. Now we're having values greater than 0, 25, 24, 25, and 60. And if we come here, we see recommended action is to add potassium sulfate based on the thresholds that were initialized in the program. So the logic is that if any of the nutrients is low, you should get a recommended action of adding. So you see the nutrients being displayed and then a recommended action that follows. So this is the short video demonstration of the working of the NPK sensor.